Genevieve speaking. In chapter 7, we used the sample mean x bar as a point estimator for the population mean mu. We also pointed out that the mean from any one sample cannot be expected to provide the exact value of the population parameter. Because of that, we compute an interval estimate equal to the point estimate plus or minus the margin of error. The interval estimate provides information about how close the point estimate provided by the sample is to the value of the population parameter. For a continuous random variable, the area under the graph of the probability density function f of x corresponding to a given interval between x0 and x1 provides the probability that the random variable assumes a value in that interval. That area is computed by taking the integral of that function in that interval. In chapter 6, we used this and the properties of the normal distributions to compute the probability that any normal distributed random variable assumes a value in any interval. And in chapter 7, we also pointed out that it is general statistical practice to assume the sampling distribution of the sample mean x bar is normally distributed. So we used this and what we learned in chapter 6 to compute the probability that the sample mean assumed a value in an interval. Now, in this chapter, chapter 8, we choose our probability or confidence coefficient, and what we're looking for are the limits of our interval. We do not know what the population mean is, so we use our sample mean as a point estimate of our population mean. If the population standard deviation is known, we use it to compute our sampling distribution standard error and our margin of error to get our interval estimate. That's when sigma, the population standard deviation, is known. When sigma is unknown, we use our sample standard deviation to get an estimate of our sampling distribution standard error. And when we do that, we end up with a t-distribution with n-1 degrees of freedom instead of a normal distribution. So our interval estimate is constructed using a t-value instead of a z-value. And that's all there is to it. The first example we're considering is that of Lloyd Department Store. Lloyd's Department Store selects a simple random sample of 100 customers to learn about the amount spent per shopping trip. It obtains a sample mean of $82. Historical data show that the population of amounts spent is normally distributed with a standard deviation of 20. A 95% confidence level, at a 95% confidence level, the confidence coefficient is 0.95, which means alpha equals 0.05 or alpha divided by 2, 0.025. So 2.5% of all x bar values are on the left tail of the distribution, and 2.5% of all x bar values are on the right tail of the distribution. Beyond the lower limit and upper limit of the interval of x bar values, we're trying to get an estimate for. Now, because we don't know what the sampling distribution population mean is, our 95% confidence interval is going to be based on our sample mean. The z-value we're looking for, z.025, is such that the probability of any z-value greater than or equal to it is 0.025. The table inside the front cover of our text gave us z-values and corresponding cumulative probabilities. And the z-value we were looking for has a cumulative probability of 0.975. Scanning through the cumulative probability values inside the table, we find the cumulative probability value 0.975. at the intersection of the row labeled 1.9 and the column labeled 0.06, which means the z-value we're looking for is 1.96. So at the 95% confidence level, the margin of error is 3.92. The lower limit of our interval estimate is 78.08, and the upper limit of our interval estimate is 85.92. If we were to repeat this exercise of drawing a sample of size n and constructing an interval estimate of our population mean based on the sample mean, each time we will get a different interval estimate, because each time we get a different sample mean. 95% of all the interval estimates obtained this way would contain the true population mean mu, and that is the meaning of the 95% confidence level. Note that we don't have to go to the table inside the front page of our text. We can directly use Excel to compute the z-value of interest to us, and we looked at that back in chapter 6. To get our z-value, we would use the norm.inv function and specify the cumulative probability to be 0.975 and mean 0 and standard deviation 1 for standard normal distribution. Let's look at a simulation to make sure that if we did repeat this exercise of drawing a sample of size n and constructing an interval estimate of our population mean based on the sample mean, 95% of all the interval estimate obtained this way would contain the true population mean mu. I have expanded our simulation from last time. So this is sample size n equal 5. Last time we used size n equal 2. I have added the computation of interval estimates, lower limit and upper limit based on the sample means, x bars. Then I use the Excel function if and nested in it the Excel function or to figure out for each interval estimate whether or not the population mean was included in it. So value in cell C5, so cell C5 is our mean, population mean. If this value is less than the value in cell F3, so the lower limit, or if it is greater than the value in the upper limit, which is stored in cell G3, then it's outside the lower limit and the upper limit, then it is not contained in the interval. And if those conditions are not met, it must mean that it is in the interval, so write down yes. Next, I instructed Excel to count how many yes I have, and stated that in percentage terms. So here with my 10 samples and 10 corresponding interval estimates, 90% of them, or 9 out of 10, end up containing the population mean mu. I have repeated this exercise for 100, 1,000, 10,000, and all the way to 50,000 samples of size n equal 5. And you can see we get closer and closer to this 95% of all interval estimates containing the population mean, as we were saying earlier. Pretty neat. Example number 2. The data on a number of weeks spent searching for a job contained in the file job search are consistent with the AARP reported number of weeks it takes a worker age 55 plus to find a job. AARP formerly stood for American Association for Retired Persons. The sample size is 40 and its mean 22 and standard deviation 11.89. So in this example we have a sample standard deviation, not a population standard deviation, so we have to rely on the t-distribution with 39 degrees of freedom to construct our interval estimate. This is a section of Table 2 in Appendix B of our text. It gives us exactly what we're looking for, the t-value such that the area or probability of any t-value greater than or equal to it is 0.025. So we find the t-value of interest to us at the intersection of that column with the 39 degrees of freedom row, and it is 2.023. So at the 95% confidence level, the margin of error is 3.8. The lower limit of our interval estimate is 18.20, and the upper limit of our interval estimate is 25.8. The meaning of the 95% confidence level in this interval estimate is the same as before. If we were to repeat this exercise of constructing an interval estimate based on a sample mean from a sample of size n, repeating this exercise many times, 95% of all the intervals constructed in this way would contain the true population mean. Of course, here again we don't have to use the table from our text. We can use Excel directly to compute the t-value of interest to us. Here are some of the t-distribution functions available in Excel. For this exercise we can use the t.inv function or the t.inv.2t function. The t.inv function returns the left-tailed inverse of the t-distribution. So to get our t-value, we specify the cumulative probability to be 0.975 and the degrees of freedom 39. Alternatively, we can use the t.inv.2t function, which returns the two-tailed inverse of the t-distribution. So we specify that the sum of the probabilities in both tails, left and right, is 0.05 and the degrees of freedom 39, and that gets us the same 2.023 t-value we were looking for. And this concludes our presentation on interval estimates.